Hello everyone. Today I am going to solve three exercises on chapter 10, exercises 10.2, 10.3, and 10.8. So these are about chi-square tests, and we are going to solve these three exercises. Will be about testing against a family of distributions, or family of distributions, testing against a specific distribution, and testing for independence. So the first exercise, 10.2, is testing against the family of distributions. Now, 10.2 says that applying the theory of MM1 queuing systems, we have skipped this chapter actually. We are not going to cover this in this class, the queuing systems. However, it's not that relevant to answer this question. What the question says is that we observe certain service times, and we hypothesize that the service times follow exponential distribution. So we want to test whether the collected service times for these, I think there are 64 such samples. I have written it here. Yeah, the sample size is 64. There are 64 observations that have been observed during 24 hours of operation. And these are the service times to finish some task, for example. And we hypothesize that these waiting times follow exponential distribution, and we want to make a test, chi-square test, to see whether they're indeed exponentially distributed. So as you can see, the family of distribution is given, exponential distribution, but it's not a specific distribution because we don't know the parameter of the distribution, which is lambda. So the first step we need to do is estimate that lambda from these observations. If you remember, in exponential distribution, lambda is the frequency, the number of events that occur in a fixed amount of time. So here, our fixed amount of time is minutes. So how long it takes, for example, on the average, it takes a certain number of minutes to finish a single service, but the lambda parameter is the frequency. In other words, how many services finish or happen in 1 minute. So it's what we have to do is, if you remember from chapter 4, the average of these is x bar, and lambda is predicted by both the maximum likelihood and method of moments as the 1 over x bar. So the first thing we need to do is, so if you just add these up, if you add those all 64 numbers and divide all of them by 64, you get exactly 5 minutes. In other words, the average waiting time for a single service is 5 minutes, and lambda is 0.2. So 0.2 events occur in a minute, all right, because it takes 5 minutes to have one service. Therefore, in a minute, there are 0.2 services. So that's what our lambda is. Now, we now turn this problem into testing against a specific distribution, whether it's exponential with parameter lambda is equal to 0.2. This estimation reduces our degree of freedom by 1 because the number of parameters in this exponential is just 1. All right, so depending on how many bins we are going to be using in our chi-square test, we are going to subtract 1 from those bins and an additional 1, because we estimated this lambda. So the first thing we need to do is, so these are the observed values. There are 64 observed values. And we are going to find what are the expected number of waiting times if we follow an exponential distribution with parameter lambda is equal to 0.2. So we are going to partition our range, our waiting times into our x-axis. We are going to partition into bins. Mutually exclusive events. These bins will be those mutually exclusive events. And since the average is 5, and we know that the exponential distribution starts from 0, so I mean you could have made from minus infinity to 2, but all the rest is 0 anyway. So we know the exponential distribution starts from 0 because it's the waiting time, which is measured in positive time units. There is no negative time, and therefore it starts at 0. What about we may try different bin sizes. This is not the only solution for this question. Basically, there are alternative solutions in which you can try, for example, 0, 1, 1, 2, 2, 3, 3, 4. But let's try these bin sizes from 0 to 2, 2 to 4, 4 to 6, 6 to 8, and 8 to infinity, and see what the expected values are that fall within these bins. Remember, the rule of thumb is that we have to have at least like 5 bins, so 6 bins. So actually, how many bins I have here? 5, I think. 1, 2, 3, 4, 5. Yeah, I have 5 bins, so I choose the minimum number of bins, what the rule of thumb suggests. And here, the important thing is the expected number of observations that fall into these bins should be at least 5. All right, so that's another rule. The number of bins, we have a rule for the number of bins. Also, the number of expected observations with these 64, the sample size of 64, the number of expected observation. How do we find that? We actually first find what is the probability to have a waiting time between 0 and 2. So this is simply if in an exponential distribution with lambda is equal to 0.2, this is simply equal to CDF2, all right, because this one, the CDF0, because the exponential distribution starts at 0, CDF 0 is going to be 0 for any exponential distribution with any parameter. So when the CDF formula is 1 minus e to the minus lambda x, so this is the CDF function, and if we just use our calculators, we see that this probability is 0.33. So the probability to have a service time between 0 and 2 is equal to 0.33. So how do we use this 0.33 to find out what is the expected number of sampling units, observations that will fall into this bin? So if the sample size is 64, this is just like a binomial in which the success probability is 0.33. So what we need to do is multiply 64 with 0.33, which will be somewhere around, 64 divided by 3, it will be like 21 or something. Yeah, it will be 21 something. So therefore, it's larger than 5. So as I said, after we decide these bins, what we need to do is we need to compute each of the expected number of counts in these bins should be at least 5. So this 0.33 probability satisfies that. 0.22 again satisfies. It's like if you divide 64 by 5, you get something around 12. So even if you have 0.1 probability, you will get 6 expected numbers in that bin. So like 0.1 is like the minimum probability we need, or maybe even less than that. So 0.15 and 0.1. So yeah, if you have 0.1, we will have expected number of items that fall into that bin will be 6.4, which is greater than 5, so we are fine. So as you see, what we did was, in order to find the expected number of items that fall into each of these bins, we compute these probabilities. What is the probability that the waiting times is between 0 and 2? What is the probability that the waiting time is between 2 and 4? Although the bins, the intersection of the bins are empty set, they're mutually exclusive. As you can see, 2 is not included in this bin range, while 2 is included here. While I'm computing the probabilities, I didn't use equality here. Let me have a pen here. So how do I do that? Yeah, like this. So as you can see, I didn't write this less than 2 less than or equal to x and less than and this equality. Actually, in order these bin sizes, as you can see, this includes 2. Actually, the reason I didn't use them was it doesn't matter, because exponential distribution is continuous. and therefore whether you have equality or not, you have the exact same probabilities at the end. It doesn't, the result you're going to get is not going to matter, because including 2 or not does not change your computation, because point probabilities in continuous distributions, they are 0. So these boundaries, the probability, whether you include them or not, it doesn't change the probability. So this is not, if you write it like that, it's not wrong. So we compute the probabilities of having service times between these intervals. After you have the probabilities, which you're going to see they're going to add up to 1. So 0.33 plus 0.22, 0.55, add that to add 0.15 to that, 0.70, 0.80, and 1.0. So these probabilities, as you can see, they're mutually exclusive and they're exhaustive. They span the entire space of probabilities, and this is what we have. And in order to find the expected times, I multiplied each of them by 64, and I get myself the expected counts at each of these bins. So 21.12, these counts, they don't need to be integers. They can be floating point numbers like that. And if you add them up, you're going to see it again adds up to 64. If you sum them, you're going to see the summation is going to be 64 in this case as well. Because our probabilities are, it may be close, some number close to 64 if you're doing some rounding to the next closest digit. So if you do something like that, maybe a number close to 64. Now, this is how we compute the expected counts to conduct the chi-square test. We compute probabilities and multiply them by the sample size. And the observed counts, we just count from here. The bad thing about this question is that, you need to go over all of these numbers one by one to see, for example, how many numbers are between 0 and 2. Not including 2. This time when you're computing the observed counts, the boundaries do matter, because since we're doing the counting, we don't want to include 2 both in this set and in this set. So if there's some observation which is exactly 2 minutes, we only want to include that in one of those bins, because we want this summation also to be exactly equal to 64. Right? We don't want to count observations into more than one bin, or we don't want to miss out any observations as well. So we do have, I guess, an exact 2.0. Yeah, for example, this 2.0 here, it is going to be counted in this bin. All right, so we simply count how many of them are between 0, larger than or equal to 0, and strictly less than 2. And there are 13 such items. Let's verify that. For example, 1, 2. So I'm just going to check them like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So these are the 13 numbers. The numbers marked with dot, they fall into this bin. Similarly, you count the numbers between 2 and 4, 4 and 6, 6 and 8, and numbers that are larger than 8, and you get yourself these expected counts. So these expected counts also look like they're like uniformly distributed, almost like, right? Is it really exponential? So there are some differences, as you can see. So we'll see whether it can be exponential or not. So chi-square test is going to give us some p-value. So what we do is, the chi-square statistic is simply, the formula is really simple. Observed count minus the expected count. You take the square of that number, you divide it by the expected count. And you do that for every bin. There are 5 bins. So you compute this mathematical expression with your calculators. You can actually have these 5 numbers, and it comes out as 6.483. All right. Now, this is the chi-square statistic we observed. Now, the next thing we need to do is determine the degree of freedom. we have 5 bins. The degree of freedom will be 5 minus 1 and another minus 1 because lambda was estimated. We use an estimate for the lambda. Therefore, we have 3 degrees of freedom. Now, what do we do? 3 degrees of freedom and chi-square statistics 6.48. We go to our chi-square table, which is on page 445. Okay, so this is the chi-square distribution. Here, degree of freedom 3. So we are going to look at the third row and look for a number that are close to 648. So that was what we found, right? 648. So if we go here, degree of freedom 648, the p-value is between, as you can see, 648 falls in between these two numbers, 781 and 625. So the p-value is between 0.05 and 0.1. So it can be considered significant if your confidence level is 0.90. So at confidence level 0.9, or for alpha is equal to 0.1, we can consider this difference, this chi-square statistics will maybe a significant enough difference to tell that this is not exponentially distributed. So if we can reject the null hypothesis that this is an exponential distribution, and we can say that this is not exponentially distributed if alpha is for example 0.1, okay, because the p-value is between 0.1 and 0.5. So at an alpha value of 0.1, this could be, so it's like in the boundary, all right. But for alpha values, so what I wrote here is that the p-value will be between 0.05 and 0.1, and it's closer to 0.1 actually. We may conclude that there is no significant evidence against exponential at 95% or more confidence levels. All right, so if you want more confidence, if you want to say that I want to be more confident that this is not an exponential, if you want to reject the null hypothesis with more confidence, you cannot do that because the p-value is large enough to accept the null hypothesis here. All right, because if the difference was larger than 7.81, so this is what the critical value is here for confidence values 95% confidence at or more confidence, you have to have more difference between your observations and the expected value. The boundary is 8.71, so your difference is less than 8.71. It's close actually. So therefore what I'm saying is that you may consider this case as at the boundary, but our conclusion, the answer is here. The p-value is somewhere between 0.05 and 0.1. It's your decision to treat this as whether this is significant or not. It really may change from person to person. This is really p-value at the boundary. But we can say that if you want at least 95% confidence, then you cannot say that this is not. You cannot say this is not exponential. All right. So it may be accepted to follow exponential distribution. All right. So this is what we may conclude with alpha values 0.05 or less. All right. So that's end of exercise 10.2. By the way, if you have any questions about these solutions, feel free to send me an email. I will try to get back to you as soon as possible. I will try to reply your emails as soon as possible if you do have any questions about these solutions. All right. Now let's continue with 10.3. This time, let me go back to the exercises. It was, I think, page 345. No, 55. Yeah, somewhere here. So exercise 10.3. Again, we have a bunch of observations. This time we have 100, a sample size of 100. Now we have implemented in this question, assume that we have implemented a new random number generator, and the generated numbers seem to be between minus 2.5 and maybe plus 2.5. I'm not sure. I mean, the generator generated a number greater than 2 and less than minus 2. Maybe it may be between minus 2 and 3. I don't know. If we generate another 100 numbers, we may observe some number greater than 3 or less than minus 3. Who knows? But this is the single sample that we have obtained, a sample of size 100. Now we are going to check whether we are going to check the sample against a specific distribution. In parts A and part B, we are going to be using testing it against two different distributions. The first distribution is the standard normal distribution. Although no parameter is given here, this is not a family of distributions. When we say the standard normal distribution, the parameters are actually given to us, which means mu is 0 and sigma is equal to 1. All right, so the distribution is specific. And in the part B, again, the distribution is specific. We are going to check it against uniform distribution with A and B, the boundaries minus 3 and 3. So is this uniformly distributed or is it normally distributed? What kind of a random number generator is it? Okay, so we may want to test it by using chi-square distribution. Chi-square tests. All right, so let's start with part A. In part A, we have this distribution, mu is equal to 0, sigma is equal to 1. Again, the first step is you need to decide on the bins. What if, let's start, okay, what if, for example, in standard normal, the center is at 0. What if I have these 6 bins? From minus infinity to minus 2, from minus 2 to minus 1, minus 1 to minus 0, and if I have something like that. Actually, if you know your z values, those z alpha values, if you remember, we have like 1.96. 1.96 was corresponding to a certain confidence level, certain alpha level. Maybe if it's 0.05, then we will have multiplied by 100, we will have exactly 5 samples, right? But it was alpha 0.05. I think it was two-tailed, so we divided by alpha by 2. So that was my mistake actually when deciding on these bins. I first thought that, okay, 1.96, that was the alpha value of 0.05. I can go start minus 2, which will guarantee that 5% is here. But actually it was for a two-tail test, 1.96, if you remember. So what happens is that the CDF value of minus 2 actually is like half of this 0.05, as you can see. So the problem is that, so what I did was, if we have these bin sizes, the probability, this is in the standard normal, the probability that x is between minus infinity and minus 2, so the probability that a number is less than minus 2 is equal to 0.02275. So if you multiply it by 100, you will find the expected number of sampling observations, sampling units that you will have in a sample of size 100, right? And if you multiply it by 100, you get 2.2, which is less than 5, which is not okay in chi-square test. Okay, we need to have the expected numbers in each bin at least 5. So these bin sizes, especially this one, is not good. We need to include more items to the right to increase this probability. All right, so we need to choose a bigger bin. So what about this this is my second try. So the first time I chose the bins, my first choice did not work because the CDF minus 2 is too small. After multiplying it by 100, the number I get, the expected number, is less than 5. So if you look at this, if I choose, what about if I go to 1.5, then 1.5 to 0.5, and then minus 0.5, then minus 0.5 to 0. As you can see, these are also interesting bins. these bins are not of equal size. As you can see, since I'm testing against the normal distribution, you can do that. The bin sizes, they do not need to be equal. All right, their lengths, the intervals. Here I have chosen a bin of length 0.5, here a bin of length 1, and the bin length on the two boundaries are infinity. They go all the way to the infinity. So as you can see, we cannot have equal bin sizes anyway in such an unbounded distribution. But if you so if these are my bins, I have 6 bins, k is equal to 6, and if I compute the probabilities to have the x between in these bins, what I get is the probability to have a number less than minus 1.5 is equal to 0.067. This time I'm fine. Multiply this by 100, I get 6.7, which is greater than 5, so okay. Now, and if you look at what is the probability to have the number between minus 1.5 and 0.5, all you need to do is look at the CDF of 0.5, subtract that from CDF of minus 1.5, which you found in the previous step already. So it becomes 0.242, even larger than this. Very good. So the expected number of items that are going to fall into this bin is 24.2, much larger than 5. Nice. And the expected numbers that are going to fall into this bin between minus 0.5 and 0 is 19.1. So this is the probability multiplied by 100, which is my sample size. I get 19.1. And the good thing, about normal distribution is that it's symmetric. Okay, we don't need to repeat the calculations for these bins, because if you see how I arrange my bins, it's exactly the same size. So 0 was the center, 0 was the mu. This other bin is exactly the same size on the right hand side of this bin, which means that the probability that x is between 0 and 0.5 is also 0.191. All right, because normal distribution is symmetric. So the probability that x is between 0.5 and 1.5 is equal to 0.242. So it's right here. And the probability that x is larger than 1.5 is 0.067. So the expected counts, which if you're normally distributed, if you have a normal distribution, if you sample 100 items, 100 sampling units from standard normal, these will be the expected number of items that will fall into these bins. All right, 6.7, 24.2, 19.1, 19.1, 24.2, and 6.7. Now, what we need is we need the observed counts in those exact same bins. The good thing about this question is that we have these 100 numbers. We don't need to go over them one by one. They're given to us sorted for our convenience. Lucky us. So, and therefore all we need to do is, for example, in order to find out how many numbers are less than 1.5, all I need to do is count them. This is the boundary. There are 8 items here, so 8. 24 items are between minus 1.5 and 0.5. Again, I need to be very careful about these boundaries. If there is exactly a number which is 0.5, I need to count it here. All right. Since exponential is continuous, it doesn't matter in expected counts here, because the boundaries will not be their point probabilities are 0. So it will not matter when you're computing the expected counts, but when you're doing the observed counts, it does matter how you these boundaries of the bins do matter. So you have to take extreme care. Now, again, we compute our chi-square statistic by using the values in these 6 bins. Observed minus expected squared divided by expected count. Observed minus expected squared divided by the expected. So if you add all those 6 terms, you get 1.886, which is a very small number. And what is the degree of freedom here? k is equal to 6, and 6 minus 1 is equal to 5. We haven't estimated anything. We didn't estimate anything, so the degree of freedom is 5. Now, here are the two things that we have computed. Degree of freedom 5, chi-square statistic 1.886. Now, let's go to the table again, the chi-square table. It was 444, 445. All right, now degree of freedom 5 this time, and 1.88, somewhere between 0.9 and 0.8, like this. Wow, the p-value is extremely large, as you can see. P-value is 0.8, 0.9, which means that you can reject this with confidence level 0.2. I mean, 20% confidence. Okay, if you want to reject this and say that this is not normal, you can do that with 20% confidence. We don't ever do such tests, 20% confidence. This is not even in the boundary. All right, so the p-value here is really large. The p-value is between 0.8 and 0.9, which means that the chi-square statistic is in the acceptance region. So we cannot reject the null hypothesis. There is no significant evidence at all against standard normal. So these values, the observed values, or the sample in this question, let's go back to 354. These numbers in this question, they may follow a normal distribution. There's no significant evidence at all against standard normal. All right, we have really high p-values. Now, so let's go part B. Is it uniform? Can we say if the hypothesis, the null hypothesis, is that, so let's have the null hypothesis saying that this is uniform. Minus 3, 3. Okay, so this is the null hypothesis. The alternative hypothesis is it's not uniform. All right, so since this is uniform and the boundaries are minus 3, 3, we will have conveniently 6 bins. If we have 6 bins of equal sizes from minus 3 to minus 2, from minus 2 to minus 1, minus 1 to 0, since it's uniform, we will have 1 over 6. The probability to fall into each of these bins will be 1 over 6. Multiply that with 100. The expected value at every bin will be 16.67, which is larger than 5. So fine, we can use these 6 bin sizes. Okay, now the expected value of the expected number of items at each bin, each of these 6 bins, is 16.67 for all of the bins, because this is uniformly distributed. Now let's look at the observed counts, how they appear in these bins. As you can see, between minus 3 and minus 2, there are only 4 items. And this is something interesting here. The observed number is 4, less than 5. Is it going to be a problem? And even here, the observed sampling units between 2 and 3 is only 1. It's much less than 5. So do we need to change the bin sizes or bin boundaries? No. Because this rule applies to expected counts only. When you're defining your bin sizes, you want the expected counts to be larger than 5. Okay, the observed may be smaller than that, so it's okay if the observed counts are less than 5. So these observed counts of 1 and 4 are not a cause of problem in chi-square tests. So now let's look at the chi-square statistic. 4 minus 16.67 divided by squared and divided by 16.67. We are going to do it for all of those 6 bins, and what we get is a much larger number. Remember, in the previous case, it was 1.86 normal distribution. The chi-square statistic was 1.86. The difference from the expected normal was not much. But we have, with the same degree of freedom, now we have 43.52. And if we go and take a look at our table again, same degree of freedom. Yeah, the largest number we have in row 5 is 20.5. So 43.52 is much smaller than this p-value of 0.001. So what I get is that from this table I cannot find the exact p-value, but I can say the p-value is less than 0.001. This was 0.001. So with 99.9% confidence, I can say that there is significant evidence that null hypothesis can be rejected. So there is significant evidence that the sample is not uniformly distributed. All right, so that's part B. And these, both of our conclusions, they're not contradicting. This is what the part C is about. So it says it's probably our random number generator here. Our random number generator is probably generating standard normal numbers. It's not generating uniform numbers. Okay, so this is what we can conclude from here. So, but the part C is asking, is it theoretically possible to accept both null hypotheses in A and B? So if we conduct chi-square tests, is it possible sometimes that we can say, oh, it may be normally distributed, or it may be uniformly distributed? Can we say both of them are true at the same time, although they're contradicting each other? I mean, a sample is either this distribution or that distribution. It cannot be both distributions in reality. I mean, if we know the truth. So, but can we accept the null hypotheses in both cases? Is it theoretically possible? Does it make sense to have something like that? And it's actually theoretically possible. So my answer that I wrote for part C is that although our current answers for A and B do not contradict each other, we could have concluded they could have contradicted each other theoretically. We may conclude that the sample might be both standard normal and uniform, because in our conclusions, when we say we can accept null hypothesis, we always give it with certain confidence level. Okay, so there is always the possibility of errors. We are not making our conclusions 100% with 100% confidence level. So since our conclusions are at some specific confidence level, it is possible that sometimes we may conclude seemingly two contradicting results. All right. So, and now I'm going to come to the last question that I'm going to solve today, which is 10.8. And here we are going to look at some kind of a variety of independence test. And the independence test is going to be conducted between 3 antivirus software. All right, so here is the question. A computer manager decides to install the new antivirus software on all the company's computers. The three competing antivirus solutions X, Y, and Z are offered to her for a free 30-day trial. She installs each solution on 50 computers. So each solution is installed on all the 50 computers, and records infections during the following 3 days. And the results of her study are in the table. So this is the antivirus software XYZ. As you can see, each row adds up to 50. Each of the solutions are installed in all 50 of them. And X found 36 of them to be not infected, while Y found 28 of them not infected. So Y seems to find more infected computers than X and Z, and Z found 32 infected computers, and it seems like Y is doing a better job than both X and Z. But is this significant? I mean, with these 50 things, can we really conclude Y is a better software? So we are going to take a look at that. So this question basically asks us, is really Y a better quality than these, or is there a difference between their qualities? So what we could do is we could actually compare them pairwise, X and Y, Y and Z, or X and Z together. But we can also try to solve the question in one shot by treating these X, Y, Z as a discrete distribution. Something can be, for example, if I just select a random software from a computer, what is the probability that it's X? What is the probability that it's Y? What is the probability that it's Z? So it's like a discrete probability, which can be a distribution, which can be X, Y, or Z. All right. And in that case, it will be discrete probability distribution with probabilities 1/3. All right. 1/3 for each. So it's like uniform discrete probability distribution in which if they're all 1/3s because they're all installed on all those 150 computers. So in total we have 150 installations. All right, I have 150 installed software in total in those 50 computers. So if you select from one random computer, one random software, what is the probability that it's going to be X? The probability is 1/3, right? So this is the columns could be one discrete uniform distribution, and the rows can be what is the probability that a computer is infected. So we have three categories here. It may not be infected, it may be infected once, or it may be infected more than once. So we can also sum all these. There are 150 findings about computers. All right, what is the probability that it's one finding is not infected? So we are going to now so we have this table, and in order to test for independence, we I mean, whether there's a difference between the quality of y being y and being x doesn't matter. We will be checking independence by chi-square test. So in order to do that, as I said, we may conduct either pairwise tests or compute a chi-square statistic for all of them together. We are going to do it this thing. We are going to conduct a chi-square test for all of them together. So observed counts are given already in the table. So these are the observed counts. All right. Two of the counts are less than 5, but as I stated in the previous question, this is not a problem in observed counts. It will be a problem though if we have some numbers less than 5 in expected counts. So how do we find expected count in this situation? I have already written the probabilities for being x, y, and z, which is equal to 1/3. So what is the probability to be not infected among these 150 installations? So what we're going to do is we're going to sum the row. If you sum the row, you're going to see that it's 68, 90, and 96. So 96. So the summation of this 96. So 96 divided by 150. So out of 150 tests in total conducted on all computers by all the software, the probability to be not infected is 96/150. So the expected count here, for example, 36. In order to find the expected count here, this is the observed count 36. What I need to do is I need to multiply this probability with this, and then I need to multiply it with 150. So in other words, what I'm going to do is I'm just here it's going to be like this, the probability to be not infected. So this is 1/3, all right, and another 96/100, and if you multiply it with 150, so this formula is actually coming from finding all those probabilities. So there's another 150 here. So this is the probability to be tested by this software and to be not infected. So the joint probability, if they were independent, we would just multiply 1/3 with this, right? And in addition, this is the probability. In order to find the count, you need to multiply it with the sample size, which is 150. All right. So these 150s cancel each other, and you end up with this, which is 32. And since the probability of being a particular software X, Y, or Z is equal, they're all 1/3s. So the expected numbers in each row, in a row, will all be equal, 32, 32, 32. Okay, if they were, and this also, this is in the case of null hypothesis. Okay, if their qualities do not differ, right? If their qualities did not differ, if being not infected is probability 96 divided by 150, 150, then we would expect 32, 32 and 32. So this 96 would be equally distributed if they had no difference in terms of their qualities, in terms of their ability to detect virus. All right, so if there was no difference, we would expect these numbers be equal, and that's intuitive, right? And infected ones is 14, 14, 14. Again, the same thing. 50 divided by 150 is the probability to be X, and 42 divided by 100. 42, how did we find this 42? The summation of this row is equal to 42. As you can see, 14, 16 is 30, 12, 42. So 42 divided by 150 is the probability of a computer to be infected once, all right, in a test conducted by all these three software. All right, now that's 14, 14, 14, and the last one is 4, 4, 4. Now we have a problem, right? If the expected number, expected counts here in the last row is less than 5 in all of these cells in the last row, so we don't want this. We want at least an expected count of 5. So what we are going to do is we are going to merge the last two rows. Okay, if we merge the last two rows, we would simply be having computers not infected and computers infected. Okay, these two categories, whether you're infected once or infected more than once, since being infected more than once, it's also observed less. All right, so, and the expected counts are also less here, 4, 4, 4. So if we merge the last two rows, we are going to just have two classes, not infected or infected. All right, and this is what we are going to do, not infected, infected. So therefore we need to also change our observed table. The first row does not change, but the last row, we are going to sum these up. 12 plus 2, 14, 22 and 18. So 14, 22 and 18, these are our observed counts, and our expected counts will be 32, 32, 32 and 18, 18, 18. So this is our table. So after we have this table, it's really easy to compute the chi-square statistic to see whether really we have enough evidence to say that, oh, Y is a better software to detect, for example, viruses on these computers. So the chi-square observation, chi-square statistic for our observed values will be the differences of each cell. So 32 minus 36 squared and divided by 32. 28 minus 32 squared divided by 32. And this is these are for the cells, the second row. And if we sum those numbers, this one becomes 0.5, 0.5, 0, and then 0. This is 16 divided by 18, which makes 0.89. This is also 16 divided by 18, 0.89, and this is 0. If you add all those up, 2.78. So this is our key result here, 2.78. It doesn't seem to be a large number, but it depends on the degree of freedom, right? So we need to also compute the degree of freedom, which was k minus 1 times m minus 1. So the number of rows, so the number of columns minus 1 times the number of rows minus 1. This is the degree of freedom for use for independence tests when we have these tables like this. All right, and the degree of freedom turns out to be 2. So we already see that p-value is between 0.2 and 0.8, but let's check that. Let's go to our table for 45, degree of freedom 2, and my statistic was 2.78. 2.78 is somewhere here, as you can see, between 0.45 and 2.22. It's closer to p-value 0.2, but it's somewhere between 0.2 and 0.8. In both cases, the boundary, we usually use 0.1 as the boundary, so it's not even at the boundary, so it's a large p-value. A p-value between 0.8 and 0.2 and 0.8 means that even at 90% confidence level, you cannot reject the null hypothesis. So there's no, our conclusion therefore is that there is no significant evidence that the three antivirus software differ in quality. So we may accept the null hypothesis that they are of the same quality. All right. So that's it. I'm going to solve. I have solved all these three exercises. In addition to this video, I'm also going to upload this PDF of the solutions on AutoClass. So take care. Next week, on Wednesday or Thursday, I'm going to upload the video on chapter 11, which is linear regression by least squares. All right. Well, I hope everyone is doing okay. Take care and talk to you next week. Bye.